I stand here, it'll catch me. Okay, so it's my pleasure to introduce our speaker and tutor today, Florian Metzer. He's from Meta in New York, and for the longest time used to work on the video team. But lately he switched to, he told me this morning, the glasses, and hopefully he'll tell you a little bit about them later. Like they're a cool device and cool product. But he's used to lecturing to students because before going to Meta, he used to be a faculty member at CMU in the Language Technology Institute. His background is interesting. He's worked on speech and language, but he's a physicist by training before that. So if you want to talk basic science to him, if you want to figure out how neural nets work, his advisor was Alex Weibel, whose paper I referred to when I gave you my introduction about how they were using neural nets in 1989. And so he knows neural nets pretty well as well. So without further ado, Florian.
Thank you, Sanjeev. Thank you, everyone. It's great to be back. Great to be here. I have a long history of working with Johns Hopkins. So we worked on various DARPA, IARPA projects together. It's been always a great time. So I'm glad to be back and to be given this opportunity to talk about computer vision. This talk, I'm giving it in my capacity as still an adjunct faculty at Carnegie Mellon. The fact that I'm at Meta doesn't mean anything today. Yeah, I think for the day we have 2 sessions of tutorials and then a lab class in the afternoon. So that's out of the way. If you want to reach me, email me at CMU. You'll also find my publications, so you can also, I'm sure, reach out at Meta. But yeah, what have I worked on and what maybe doesn't necessarily qualify me to speak to you here today, but why did Sanjeev pick me to speak to you today about computer vision? I've worked on low resource end-to-end multimodal automatic speech recognition at CMU. I've done a lot of work, and I realized that speech recognition with neural networks, everything becomes a sequence model. Speech to text, well, this is too easy. Can we make it harder? So I started to work on video retrieval and video summarization. That was the topic of some JHU workshops. I've also co-founded a startup in Pittsburgh that summarizes medical conversations. That company, Abridge, still exists and is doing really well. But yeah, since 2020, really, I'm at Meta in New York. I supported a team called Multimodal Video Understanding, and we did recommendations for IG Reels. So when Meta started Reels as a competitor to TikTok, baseline recommendations at Meta always come from your social graph, so we know who your friends are, and we show you the materials that your friends have seen. But what TikTok does and what Reels tries is to give you recommendations that you are topically interested in. And so this becomes a content understanding problem. And my team did a lot of the basic content understanding work on text, images, videos, and audio for that. But yeah, for about 4 weeks ago, I switched to the team that works on the Ray-Ban Metas, or on the Ray-Bans, the glasses that look like sunglasses, like regular Ray-Ban glasses, but they have a microphone, they have cameras, and so you can ask questions to them, you can have a conversation with them. They talk to a Llama language model on the back end for chit chat. They talk to a multimodal Llama model in the back end. And so if you take a picture and say what wine goes well with that food, we'll give you a recommendation. And I'm very excited about this product, and I think you should try it too. It's a lot of work still for us to do. If you've seen the OpenAI GPT-4o demo 4 weeks ago, we are not quite there yet. So if anybody is interested in working on that, and you're graduated and you're clear, feel free to give me a call. So what I want to do is talk about computer vision, and assuming that many of you have language background, speech background, sort of relate a little bit my experience of working in these fields. How do they compare? How are they different? And then walk through some seminal aspects, seminal papers, some important topics of current computer vision research and technology. Now, when I started out, I looked at speech and said, oh, speech is so nice. It's 7,000 different languages. It's a really cool problem. But what I found out when I worked in industry is that, well, few really care about all the 7,000 languages, unfortunately. A lot of it is just retraining on foreign data. We run the same methods on multiple data sets, and it works well enough. We have very few tasks. So we have in speech, we have speech to text, we have text to speech, we have keyword search, spoken term detection, we have paralinguistics and language modeling. But that's maybe it. And then we have a lot of techniques such as enhancement, robustness, multilinguality, discriminative training, weak labels, to do that. And so in computer vision, by contrast, there's really only very, very few conditions, which I sort of would compare to the languages. So there isn't really a specific computer vision for low light work, or for now there's work starting on egocentric videos that tends to be taken from a higher point of view than regular photographs. So people are specializing, but there is a huge amount of tasks. So there's image classification, there's object detection, there's localization, semantic segmentation. So if you have an image, there's a lot of different things that you can do, and these all come up as different tasks in the field. So even things such as crowd counting are its own discipline with its own evaluation and its own standards. So there are people who specialize in taking an image and quickly counting how many people can you see in that image. And that as a speech researcher, I was like, wow, there's just so many different things that people do in computer vision. And of course, they have their own techniques. Some of them overlap with us in speech, contrastive and self-supervised learning, images versus video, stereoscopic vision, but it's very distinct. Also, I think because of these many tasks, tends to be a much bigger community. So citation counts in computer vision are on average much higher than say in speech. So I think the last time I checked, the Caldi paper had 7,300 citations, and sort of your random computer vision paper, you only look once before, which is a famous object detection model, but it's only one of several object detection models, and it has 16,000 citations. So don't get frustrated if you compare it. That's just the way it is, and not a. I'm telling myself that this is not a measure of impact and importance if you compare citation counts just. I want to argue that the computer vision community also has huge misses compared to, say, the speech community. So it looks like robustness, for example, is something that the speech community has worked on for a very long time. But computer vision in 2022, they realized that, oh, if we take egocentric visions, if we have cameras that people wear on their heads, the way the image looks like is very different from standard photographs. And they found that regular models that were trained on standard databases didn't work well on egocentric videos. And so they collected 3,700 hours of video. And as a speech researcher, I said, well, who knew? But it took the computer vision community until 2022 to sort of discover that different microphones or different camera placements have an impact, and then they start collecting lots of data. Also, I want to say that stationary signals, images, for example, are much easier to work with simply because they have a fixed length and you don't have to deal with a variable length, which makes fitting them onto GPUs much harder. And also images have a lot of information, so it is very tempting to work on video, but for practical purposes, it's very hard to find use cases where video information adds a lot of information over just image information. Handwriting or sign language may be a big, probably is a big, is not the case here, so you're safe. The interesting thing, though, I think, is that there's a lot of vision and language work happening now where people are trying to bring together visual information, text information, or audio information, and I'm very excited about this work. So what I want to do today is talk a little bit about standard computer vision tasks, dataset techniques, then present some models that are important in computer vision, talk a little bit about representation learning, self-supervised learning, masked autoencoders, and then spend that's probably going to be the first part, and the second part talk about image text learning, so modern computer vision that sort of blurs the line to NLP and speech a little bit, talk about foundation models, which are becoming which are a huge thing in computer vision these days, and finally talk a little bit about fairness as a general topic in AI or machine learning, but here specifically with the context of computer vision. Any questions so far?
Maybe about the Meta glasses. Like we were googling them already, so they are on the market. And what are the capabilities? Would you recommend to wait a bit or?
Of course, there's going to be new versions coming out. There are timelines. Maybe they're accurate, maybe they're not. But I think the current glasses that are on the market have a lot of life left, and there will be a lot of new capabilities added just by software. So the current glasses, they can do dialogue, they can do multimodal analysis, but there's a lot of stuff coming, so don't hesitate. But I think, I mean, we are selling more than we can make. So if you can have one, get it. I should have brought one. I should have brought my own pair, I'm sure. Yes, sorry.
As for the headset with the inside, right? Is the sound good or the sound?
I like it. It's good. I mean, it's not quite the same sound as the Quest, where when you turn around, the sound stays the same, and you really have a spatial experience. That's not the case with the glasses, but when you wear them to listen to music as a headset, I think the quality is great.
Sizable show that can be have a much less citation than the random paper in computer vision. And you said that one of the reasons is that there are much more tasks in the page. And I was curious to know if the reason is more about like the difficulty of the modality, because like speech is kind of difficult to deal with. Like if you're a beginner, it's much more easier to learn about images and to process images than speech. And don't you think this is the main reason of why the speech community is much smaller than the computer vision one? Or is it not the
Yeah, I haven't done a proper study, but my impression is that just because there's so many different things that people work on, the community is just very, very large, and people, if somebody does something on one task and the method gets ported to another task, then that gets a citation. So is it more difficult or hard? I don't know. I don't want to judge. But of course, you find many computer vision tasks that are sort of saturated, but there's many as a speech, but then there's many tasks where people are still actively working on. So I think just when I was an undergrad, I said, oh my God, speech is so cool because there's 7,000 languages and they're all different. And but now I realized that, oh, in these different CV tasks, you actually use different methods. You do the specialization there, and that doesn't really exist in the speech community. Anything else?
Maybe I just wanted to add, and maybe you can refine my answer, but vision is like the main perception of the world for humans, right? And it's like dominant. We were taught this, that it's like 95% of sensory impulses from the world and the environment are processed by our vision apparatus. So maybe that's somehow also related, that we as humans are simply more attuned to see the world through the vision than through other senses.
Possibly language people will tell you that all the knowledge in the world is being encoded in language. But yeah, for sure. Yeah. So if there's any questions, just feel free to interrupt me. We can do this interactively, I think. All right. So this first part largely follows a class from Freeman and Isola at MIT. I don't think we really need to motivate computer vision. It is the fundamental modality by which humans perceive the world. And of course, it has its own myths. Speech recognition people, you may be familiar with the idea, the urban myth that in the 40s or 50s, when researchers discovered speech recognition through spectrogram matching, you were looking at spectrograms, which are time versus frequency plots, and you can look at it and you can actually read speech by looking at spectrograms. Then there was a summer project. We've got the boy working on it, saying, oh yeah, we'll figure out automatic speech recognition by teaching a machine to look at these spectral dynamics and figuring out what it means, because you can see there's clear phonetic evidence of where there's a fricative, where there's a burst, and then you have a lexicon and you have speech recognition. Computer vision has a similar urban legend where apparently in 1966, Marvin Minsky asked Gerald Sussman to connect a camera to a computer and do something with it. And that was supposed to be, this student summer project was also supposed to solve object identification in an image, which is one of the fundamental computer vision tasks. But similarly, that also didn't get very far, but sparked a lot of research over the years. And maybe now, 50 years later, we are somewhat, we have made a lot of progress, and we may think that with recent methods, we may have solved the problem to some extent. So why is computer vision hard? Well, let's look at egocentric videos or egocentric images, and let's look at historical images, paintings. Why do you think what's the problem in these images, or what strikes you when you look at it? Yes. So exactly, I gave it away a little bit by adding this image. You can see that artists over centuries were really trying hard to say, oh, we have things that we know are square here, but we know there's depth in the image, and how do we figure this out? There's parallel lines here, there's parallel lines here. But in their attempt to project them into space and have different layers of depth in an image, it comes out wrong, and nobody really could do it right. of course, you can do it right in simple cases when you're projecting everything to 1 point or you're projecting everything to 2 points. But a general perspective is, and a real approach is very, very hard. I don't want to give a photography lecture, but that's really sort of the deformation of objects when you see them in different perspectives really makes it hard. And only when researchers essentially in the Renaissance painters, Da Vinci or Vermeer, had access to cameras and camera obscuras, where they sort of, which helped them get perspective between objects, right? Then did humans figure out perspective and were able to generate perspective. But the fact that it took us several hundred years to get it right shows that computer vision, similarly to speech, has its own difficulty in that the way you look at an object changes depending on how close it is, how far it is, and it's not self-evident. Consequently, just a few years ago, I'm taking this from the Isola Freeman lecture, objects of interests had different sizes, aspect ratios, lighting was different, and yeah, as a consequence, apparently this was a early computer vision system that misclassified bathroom objects as horses, sheep, and airplanes. And a lot of the research was spent on getting the multi-scale aspect right. So saying, is an object close to me? Is it bigger? Versus is it further away? Is it smaller? But not so much dealing with perspective, the robustness of the observer, and so on. However, in the last few years, a lot of progress with neural networks, a lot of progress has been made. Computer vision tasks go from simply detecting objects, which is sort of what you can see in the top. We can see that there's surfboards or people, and we add bounding boxes to them, towards actual segmentation of an image, saying there are certain objects in an image, and we can accurately segment the image into what are the objects, where's the wine glass, where's a person. A lot of this had to do with large data sets where we have supervised learning or weak labels, similarly to, I think, what we're doing in automatic speech recognition, where we use hidden Markov models to align labels to the data. So we only know what the words are in an image, and we use hidden Markov models to align the word sequence to the audio. Similarly, a lot of computer vision work uses weak labels to say, oh, we know what objects, or we assume what objects are in an image, and then we let the model figure out where those objects are visible and which part of the image they take. And a famous example here is the mask RCNN model. Then there's other models that sort of learn semantic relations between objects, but I think the big huge progress was made with the CLIP model, which brings together images and text, and we'll talk about this later. Yeah. While I was thinking about which tasks to talk about, I was really having a hard time to pick, and so essentially I just want to give you the best reference that I was able to find, which is this Viso AI website that sort of has a nice overview of what computer vision tasks exist, what techniques are being used, what leaderboards, what evaluations exist, how closely are they, or how close are they to being solved or not, what are the trends in these directions. So I want to invite you to look this up in India. Are we sharing slides, by the way? Or I'm happy to share those, so you don't have to scribble it down. We can. Okay, good. So here's a typical example of a leaderboard of an evaluation in computer vision. This is the Kinetic 600 database, which is a action recognition data set that's used very frequently. And so the important things are much, I mean, like in any discipline, standardized training and testing conditions. Many of these evaluations have become saturated over time. So you can see that there isn't really a lot of, between January 22 and January 24, there has been progress on Kinetic 600, but not drastic progress. What's also important is that you need to pick the right one for your needs. So if you're working on a problem, you need to understand which of those standardized benchmarks fits as closely matches your problem. Because when you look at the published literature, everybody beats some benchmark somehow, somewhere. And you need to understand if it's the right one that you're working on. Before going into details of models and tasks, I want to be clear that what am I skipping? I mean, there's a lot of work that I won't be able to cover. I'm not doing, I mean, even to the introduction of computer vision, I'm not talking about cameras, projection, signal processing, but also more generally, I'm not giving an introduction to ML and AI. I'm not talking about applications. I'm not talking about generative approaches to computer vision. I think Marek is going to talk about that a little bit. And I'm also not talking about anything like edge computing or dedicated specialized approaches. All right. So let's look at computer vision models a little bit. So really what I mean is convolutional neural networks and vision transformers. So the backbones of most computer vision systems these days. Now, in computer vision has had the ImageNet moment, which is sort of one of the, who has heard of it? Let's start this way. Okay, then I don't need to talk about it. But it's an interesting thing that, yeah, in 2012, a lot of activity in deep learning was started when people realized that a convolutional neural network had won the ImageNet challenge, and not just by a little bit, but by a significant margin. So I think this was really made it clear that computer vision methods, or that neural networks were able to help computer vision, made significant progress in computer vision, and this had a huge impact on the CV field, but of course also on other fields, and that people started to take neural networks much more seriously again. Of course, I couldn't not mention that computer vision hasn't invented convolutional neural networks. Speech people, Alex Weibel, published about a time delay neural network in December 1987. And the first reference to a convolutional neural network, Yann LeCun's work, is in 1989. So I think we're not taking away anything from both of these achievements by pointing out that the fundamental realization that what you need for both speech recognition and computer vision is translation invariance and sort of detecting edges and detecting visual features. And that's exactly what the time delay neural network and the convolutional neural network does. But yeah, speech people invented the convolutional neural networks before computer vision people did, even in 2 dimensions. Marek.
Yeah, it's like it was done on spectrograms or the waveforms.
It's the spectrograms.
Like visually observed
data. Yep. Yeah. So I mean,
just one 2D representation.
Find out.
Yeah, I mean, the challenge, of course, is that in speech we have the time axis and we have the frequency axis, and they're not the same. So the types of distortions that you get on the time axis is different from the types of distortions that you get on the frequency axis. So the speech work started, I think, on the time axis only, and then was expanded to the second dimension. And it was a little bit more handcrafted in the sense that there's no rotation invariance. Speech vision started from a rotation invariant perspective and treated it all the same and formulated it maybe more elegantly because of that. But the core realization is the same, that you want to detect features, and if they're shifted a little bit, doesn't matter. And so you have those detectors, and then you pull them, and you have detectors and pull them. You stack this on top of each other until you have your whole representation learned. Make sense?
Yeah, I'm just curious because was it the data for the phoneme recognition? Because it's generally a continuous signal, so it was like a sequence processing approach.
Yeah, so for speech recognition, we typically take the time signal, we do a short-term Fourier analysis. So we have a windowing function, we cut out short signals. We assume that they're pseudo-stationary so that they repeat, and then we do frequency analysis. We get a spectral representation, and that's.
So do we classify like the microsegments of the speech? We do classification, or was there something like more?
Didn't we have a speech lecture already?
They did phoneme classification, one segment, one phoneme.
Yeah, so
Right, in this case, it was phoneme classification. So you take a slice and you classify it, but then adding a hidden Markov model on top of it to do the time series modeling is independent of this here. All right. Yeah, I think I did prepare some motivation about computer vision and how we can derive the convolutional neural network. But I think the show of arms that you're familiar with the ImageNet moment, I think most people are familiar with convolutional neural networks. Do we? Right. So the realization is that we have input patterns, and both in CV and in speech, it doesn't really matter where exactly they are in the image. What you want to do is detect characteristic features like edges and similar characteristics. And so if you can build a network that's robust to shifts in the image, and if you can build a network that's sort of robust to deformations to some extent, you can improve the detection. You can build much smaller models. You can train them with a lot less data, which was very important at the time. And even this earlier model that Fukushima built has those elements, but it did not have training with backpropagation at the time. Now, when you built, or the important thing in this model is that you have separate layers. You have feature extraction layers that sort of build a localized representation of very small patches, if you will, and learn many different detectors for local shapes, and then you pool the output of these layers in separate pooling layers, and you can do average pooling, you can do max pooling to sort of look at a bigger region and learn a representation to say no matter where exactly a certain peak is, you're getting the same signal. And Fukushima's model already in 1980 could do this. And once we added backpropagation in Weibel's work and LeCun's work, then we have what's known as the convolutional neural network, where we are stacking many of these recognition layers and pooling layers, or feature detection layers and pooling layers on top of each other before we add a few dense layers at the very end to build the output representation. So all we have to do now is when we have an image here, the number 9, we can train this entire network from in a supervised fashion with backpropagation, and we have an end-to-end trainable structure that'll learn. I think I have maybe I did. Oh yeah, we have an end-to-end trainable structure that allows us to learn feature maps and then also look at these feature maps that sort of show us what types of representations does the model look at. And so you can see that the standard computer vision models, they learn to detect certain edges, horizontal, vertical, or even diagonal, and they are also sensitive to various color schemes depending on what the training data is. Yeah. Over time, really, once this was invented, really everything that you needed to do is scale them up. And so this LINET 5 was an architecture from the 1980s, and this AlexNet that won the ImageNet challenge is essentially the same thing, just on a much, much bigger scale. So the input image has a higher resolution. There are more intermediate layers. There are more feature maps. In the end, you have a much bigger model, but fundamentally, it's just the same thing. And if you think about if you're looking at it from a simple, let's say, neural network way, all you do is take 3D arrays, because in computer vision you have height, width, and you have 3 color channels, red, green, blue. So you're mapping this into a 3D array, you're flattening it, and then every network sort of maps very easily to a simple neural network with sort of linear shapes. There's a lot of tricks and a lot of work has been done in computer vision to figure out the best way to train those networks, and there's very interesting or very creative ways of plotting neural networks. One of the big tricks also was realizing that we need to drop out weights, that we need to train neural networks with take more motivations from the human cortex, or from the way humans learn, or we believe humans learn by dropping out weights during training. Otherwise, we're getting significant overfitting. But fundamentally, we are able, convolutional neural networks, we're able to train very large but very simple networks very effectively on large amounts of data. And this has sort of given a lot of, led to a lot of progress to in computer vision, but similarly also they have been the backbone for speech recognition for many years. What's important, or what's good to remember, is that neural networks are sort of an architecture that's inspired biologically, and it's sort of suited well to computer vision problem by explicitly sort of modeling the visual cortex and saying we're learning filters for local features, which we're then pooling. And when transformers came around, there was a lot of interest in saying, oh, what are the types of biases and inductive biases that a transformer might have. And if we are able to train computer vision models with transformers, are they going to learn the same types of biases and or not? And how do transformer models and CNN models compare? So the work on this has tapered off a little bit, but it will be, I'll show a few examples, I think, about how a neural network architecture that does not have these built-in biases learn versus a CNN model. Any questions on CNN so far? All right. So, of course, we had the ImageNet moment in 2012. Then later we had transformers. Attention is all you need. 2017, 2018, the BERT model. Now, computer vision researchers, of course, also looked at this and said, well, here we have this architecture. How can we use this for computer vision? Of course, it works. We can apply transformers also to computer vision. And the first work that did this successfully was known as the Dieter detection transformer, where we have a transformer encoder and a transformer decoder that predicts objects in an image and is similarly trained end to end. And in this case, the researchers used a CNN backbone to sort of produce a set of image features, which they then simply divide into patches and put into the transformer encoder. So the first attempt with Dieter didn't completely put away with convolutional neural networks. Researchers felt that at the input, or they were getting better performance when at the input they used a CNN to transform visual features into more general patches, added positional encodings, and then fed it into a transformer. But it was a very elegant architecture in the sense that it allows you to produce objects and detections in a decoder where in this case, it was not a sequence prediction problem, but they predicted all those objects as independent predictions, not as a sequence. But the first attempt already showed that this detection transformer outperformed the standard object detection approaches by a large margin. And so it showed that transformers would be very powerful in computer vision, but it did not do away with convolutional neural networks entirely, and it sort of was applied to a specialized problem which you could cast as a generative problem by predicting objects in an image and bounding boxes. It was also somewhat unorthodox but I think the biggest advantage of this architecture over standard models was that it didn't need to suppress near duplicate detections and does not rely on anchor boxes. So because it's a generative approach, you're sort of saying, give me a few objects, and the model then decides where it puts those objects, rather than starting from the bottom up where you detect candidate regions for certain objects and then you merge those together, which is sort of a source of error. Dieter didn't have to do this and therefore was able to outperform standard object detection approaches. It's also worth noting that a standard state-of-the-art object detection framework, the YOLO v5, for example, is a hugely complicated structure of many convolutional layers, where we are then extracting features at different levels of the stack of convolution layers to be able to extract and detect objects that are close, far, and in between. Yes. In the Dieter model? Yeah, good question. So they include a bipartite graph matching algorithm in the loss function. So it figures out the best way to divide the permutation, or to solve the permutations, and there is a hard limit in the model in the maximum number of objects that you can detect. So that's why I'm saying it's a little unorthodox, but if you know what the training and test data is like, then you can engineer it. All right. I think Mark is going to talk a little bit more about Dieter tomorrow, or
I mean, I will adapt as you go, so I already have some ideas.
good. Cool. So this was the first attempt at using transformers in computer vision, and it was sort of not going all the way. It was sort of halfway by it maintained convolutions, and it used a specialized setup, but it was clear that the transformers were also useful in computer vision. And so the main architecture, the main backbone for computer vision now is vision transformers, and the paper is for that is an image is worth 16 by 16 words, which sort of plays to the fact that it turns out all you need to do to train a good image model with a transformer is essentially divide an image into patches by 16 by 16 pixels, and then flatten these patches by sort of converting a matrix into a linear vector, converting the 3 color information into three numbers that you just append, and then doing a linear projection to a smaller embedding, and feeding this into a transformer, adding positional encodings to break the symmetry, but you don't need positional encodings in vision transformers. Don't encode actual position in a two-dimensional sense, so you're not even maintaining the neighborhood relationship, but models figure it out. And what researchers found is that particularly with large amounts of training data, you can apply a transformer architecture to computer vision problems. Specifically, if you, for example, Google, who wrote this paper, they were using a data set of 300 million images, which is 2 orders of magnitudes bigger than I think most other computer vision databases at the time. But by doing weakly supervised training on this large data set, they're able to train a very general architecture such as the transformer to beat CNNs in essentially all computer vision tasks now. This took in the original paper, they're saying they're training their model for 30 days on 8 TPUs, 8 TPU servers. So it's a massive compute effort, but still being able to train a very general architecture without any inductive bias towards what features are important for computer vision problems is very interesting, and I think a huge achievement. Yes.
Flattening images is expected. Is that taking the like red, green, blue channel and compressing that down into one?
No, you're just appending them. So it's like you go through the image line by line, and then you do red first, then green, then blue, or you're interleaving it. I'm not sure which one they do. You're just concatenating. Yeah.
Well,
I mean, like, the results for it doesn't matter, right? Because one of the features anyway is so efficient. As long as the position coding are associated with proper levels of patches, doesn't matter if what order the patches are fat as the input.
Right. I mean, what you do is you have a projection layer. So no matter what your inputs are, you're projecting it down to a 700 dimension, 706, is that it? Yeah, so a 768 dimensional vector, and that's all you retain. Then.
I wanted to ask about your opinion on this because when I was reading the paper, I was very disgusted, let's say, by the approach of patchifying the images, and I was like figuring out why are they getting rid of the CNN, right? Which is so good in translation, equivariant, and so on. And they also had a footnote or an appendix that they tried it and it was worse. But to me, they only beat ResNet after using the pre-training on the 300 million images, which actually was the funny story about it was an anonymous paper, but only Google had access to GFT data set, so it was not that anonymous.
There goes anonymity. Yeah.
Like, is this scaling approach the good way to go? Like, just throw a bunch of images on it and it starts to work, or whether we should like try to engineer the processing? I'm asking about just your personal opinion on it.
Yeah, so I'm going to talk about it in a little bit.
So then what's my head?
Anybody else? All right. Yeah, so this basic VIT model, it works, but yeah, it's very computationally expensive. And because the stack is sort of, you have the transformer stack, it doesn't get, there's no hierarchy to it. It doesn't get smaller as you have higher layers. So there is no bias towards aggregating information over the entire image. You can just simply learn transformer layers over transformer layers. So there has been a lot of work in trying to find architectures that maintain sort of this concept of hierarchy, to say at the lower layers, we have many small patches, but then what we can do is simply append multiple patches together and have fewer but bigger patches and sort of have a pyramid structure in our transformer, and get a transformer that forces the creation of patches that aggregate more information across the entire image rather than only on small bits. And so these are multi-scale vision transformers, and they obtain state-of-the-art performance on both image and video tasks, and they're much more efficient in computation, because in the higher layers you're reducing the number of patches and do not require large-scale external pre-training to be competitive. So these are important considerations for practical applications when you run these models at scale. And this is one example from Meta, but there are related examples, and further improvements where you're adding various types of pooling attentions, pooling networks, to aggregate information from those at different levels of how do you say, this pyramid where you're converting many small patches into fewer bigger patches. So there's a lot of work in improving architectures for transformers. And essentially what you're doing here is you're adding a little bit more of your bias and your expectation back into the model to make it train faster, make it train on fewer data, because you know what type of information the model needs to look at in order to do object detection, video action classification, and so on. Why is this a little bit frustrating? And what's the challenge here? Well, BERT or ImageNet or transformers are a very simple, very general backbone. And we can now add our model bias, or we can add our biases back into the model by shaping the model in certain ways and turning it into a pyramid rather than a stack of identical layers. And we are doing this because not everyone has access to a huge supervised data set. Now, but what if we could do pre-training with self-supervision, which is essentially what BERT does in the language model, and where it's at least you still need lots of data to pre-train the model, but at least you don't need labels for that. And so this is what I want to talk about next. Sort of what are the ways of pre-training these models in computer vision? How can we learn representations in computer vision using either weak labels or self-supervised learning? This is a lot of this is taken by a talk from Xinli Shen, one of my colleagues at Meta. Now, any questions on CNNs and transformers so far? All right. Now, in NLP, a lot of the gains came from being able to take a very general structure and then pre-train it on large amounts of data and use this pre-trained model in many downstream tasks. And so the same thing you want to do in computer vision as well. You want to take a model, pre-train it on data, and then apply the representations that you've learned on many different downstream tasks. And if you do things such as supervised pre-training, which is what the original vision transformer paper did, probably you're biasing the representation that you have towards classification tasks, towards things that are inherent in the model and inherent in the labels that you used for pre-training. So if you want to do different things, such, for example, build a chatbot, detect and segment objects, predict the structure, then you want an unbiased and probably an unsupervised learning methods. And so we can do self-supervised learning, starts with only given data. How can we learn representations? Now, there's two ways. Often, or we can frame the problem as having two potential solutions. One is the autoencoder, one is the joint encoder. The joint encoder, of course, being similar to contrastive learning, where we're modifying one, we are taking our representation, we're modifying it, and we're learning a model that says, is this the same original input or is it not? Versus the autoencoder being a representation where we have our input data X and we want to reconstruct X from a distorted or reduced version of the input, so that the model learns to rely on the important features in the feature because it's able to reproduce it from a corrupted version. So the vanilla form of an autoencoder is really, of course, take the full data as input, take the full data as output. Now, that's, of course, trivial. That can be done. So what we could do is add sort of a bottleneck layer there to make the task harder. And the encoder learns to predict the bottleneck representation while the decoder reconstructs the original output from the original signal from the bottleneck representation. And before the deep learning area, there were many examples of this: PCA, k-means clustering, other variants such as matrix factorization, matrix decomposition were used, but all sort of follow the same shape or have the same idea of taking a signal, corrupting it or reducing the dimensionality, reducing the information, and then reconstructing the full signal from it. And if we do this well, then we have learned a good representation of the input. Now, the problem, of course, is that simple autoencoding, it is sort of too easy to cheat. We don't know, or we have no good way of controlling what the model learns in order to reproduce the input. But so what we can do is introduce meaningful constraints that encourage the model to learn those characteristics of the input feature that it turns out are important and relevant for not just for reconstruction, but for the downstream tasks that we're actually interested in. So we will introduce extra constraints on the dimensionality, on the clustering, on the quantization, or extra regularization to make the simple autoencoder work better. Now, for computer vision tasks, there are a few things that we typically do. So we can learn certain transformations, for example. So if instead of just the leading parts of the input, we can rotate it, we can teach the model to learn rotations and learn rotation invariants on the input, so that any representation that the model learns it becomes more rotation invariant and sort of is better able to encode such information, which will then be useful for downstream classifications. We can, instead of rotating the image or parts of the image, we can also do tasks such as predicting the relative position of patches of the image, or predicting what types of rotation we apply to the input image. We can also do standard denoising. Denoising autoencoders are a frequently used approach in computer vision. And we can even do tasks such as colorizing the image and predicting context, predicting neighboring frames, and so on. So there is a huge, depending on the type of input, is it images, is it videos? People have tried a lot of different tasks and combinations of tasks for autoencoders. And but fundamentally, the same principle that applies to BERT is to say, can we mask out part of the image? Can be applied to computer vision, and we can use the masked autoencoder principle or masked language modeling principle also to pre-train large transformer models for computer vision tasks. So the core idea really is going to be, can we do self-supervised learning with masked autoencoders using a transformer backbone and reconstruct the input from the entire input and the uncorrupted input from the context that's provided. Now, what is the big difference from text here? Well, in images and even in video, we have a lot of redundancy compared to text. I think standard BERT training masks out about 15% of the token. In image masked autoencoder training, typically we're masking out about 50% of the tokens. And in video representation learning, you can even mask out about 90 or even 95% of the tokens, because there is just so much redundancy in the signal And if you don't mask out really high amounts of data, then the model, the task becomes too easy. And even though you're adding transformations, the task becomes too easy, and the model, just doesn't learn as well as it can. Specifically also for videos, there's very interesting, let's say in text, we are randomly masking out words. In images, or specifically also in video, there's different strategies that we can use. So if we have a video here, we have the width, we have the height, and then we have the time axis. So there is sort of a strategy to do random sampling, and you only keep those random patches, but you can also do things such as space-only sampling, where you are picking certain points in time, where you're picking certain pixels or patches in an image, and then keep those images over the time axis. Or you can do time-only sampling, where you are only looking at certain points in time, and the model sort of needs to reconstruct the missing frames. Or you can do some block sampling, where you are sampling bigger blocks according to certain criteria, and masking out others. Now, in different works, I don't think the jury is really out yet which of these sampling strategy works best for all tasks. Some papers find that space-only sampling works really well. Other papers find that sort of random sampling works really well. My own impression is that it depends on the task that you have, if there's camera motion involved. But those are, I think, still open questions. But it's important sort of to remember that in computer vision, because you have different axes, different sampling strategies may be necessary, while in text you're simply masking out random words. So here are some examples of what does 90% masking ratio mean for a video. So in individual frames, this is sort of the input that you give to a masked autoencoder to predict an entire video, and the models are able to learn the best representations from these inputs. So 90% masking ratio is really high. You're only giving very small bits, but because of the high redundancy, and the model has the entire context to make the prediction, it works well. There was a question?
It's hard to predict the next frames, and don't you think that the model is trying to learn the average, not really trying to learn like to compare?
Sorry, can you rephrase, please? I'm not sure I fully understood.
Sometimes some loss will makes a model to learn the average of the image, not like don't really learn how to exactly reconstruct the image. And I was kind of curious to know what's your intuition behind the fact that we can mask the image with this ratio, right? Because it seems to be very high. And I'm kind of curious to know what's the intuition behind it, and how can the model learn really well to predict the image.
Oh, I see. Okay. Well, when you want to give the model a hard task, because it needs to learn the salient, the important features, and if all the model has to do is here's an image and here's an image, and they're not that different, and all it has to do is fill in the same image between those two, then the model doesn't really learn a salient representation that sort of tell, in video case, for example, models the trajectories that objects typically take in a video. And this is what you need to learn when you want to do video action recognition, right? So the model needs to learn that doors close or balls fall to the ground. And if you give it too many frames, then the model just says, okay, well, all I have to do is copy this from here to here. And it doesn't learn that, oh, motions happen in certain trajectories over time, that the ball accelerates and so on. And therefore that's why you need a higher masking ratio. I mean, all these values were sort of determined by ablation experiments to say, let's try different ratios, let's try different augmentation strategies, and then see which ends up giving us the best representation, which we can then fine-tune for downstream tasks.
Another way to it is that I think you're puzzled by the fact that 90% of the data is missing, right? But think of it this way. Imagine that I give you 1 second of this video, and that 1 second has 30 frames. And I give you 10% of each frame. I've given you 3 frames per second. What can you do with 3 frames per second? Instead of 30 frames per second. Is that little information, or is that enough to reconstruct the data? So,
Well, but we need to account also that this works for still images also. So not just in videos, but I think the original paper masked 75% of the image, and they get the best results, even better when they mask less. So I actually get the question, but I don't have the intuition how it is able to do, because the loss is just mean average error, right? So it could like collapse, right, into some average grade or whatever, but it does not, and I'm not sure.
Well, but I think the important thing to remember here is that we are not measuring the reconstruction loss, or when I say the best masking ratio is 90%, of course the reconstruction loss at a masking ratio of 90% is high, so the model doesn't perfectly reconstruct the missing patches, but the representation, the internal representation that it learns when you're trying to reconstruct 90% of the input data, the internal representation is best when you then fine-tune this model on downstream tasks. That's what we're really interested in, right? Of course, reconstructing only 2% of the data is easy, will work well, but then the student hasn't learned anything, right? You need to challenge the student. Sorry, I forgot who was next. Fiona.
Intuitively, if you give a person an image, about 75%, they would not necessarily can reconstruct the image. So is there any concern over how the model is learning it, and whether the kind of, because you cannot interpret what the model actually learned? Is that a problem?
Right. Good question. I'm not aware of any work that tried to dissect what the model is actually learning and how the model is making the reconstruction. As long as the model is able to do it, we're happy. And many things here are counterintuitive in the sense that you apply a really brutal patchification initially, and then you don't maintain localities. So we have a 2D image, but the only thing that the patch, the local, what are they called? position embeddings, the only thing that position embeddings do is break the symmetry, allow us to distinguish different patches that otherwise look identical, to distinguish them from each other. The position embedding doesn't tell me that this patch is below this patch, because I don't know how many patches or the model itself doesn't know how many patches go across and how many patches go up, down. So I can imagine that from a CV researcher, these are all deeply troubling developments. But simply pre-training a model in this fashion seems to work really, really well.
Not only that, they also have some tokens where they use the wrong word and let the model identify that. Would that also used in image training, or is it just match on it?
Yeah, so they're doing the same thing. They're rotating some parts. They are the same techniques are applied here, and it helps similarly to what BERT what's done in text. That's correct.
Makes the model learn all the G for the one. Do you keep the model works or not like
Well, you should really ask Gianluca. But I don't think it does.
I would say are complex. Like the question was, why doesn't it learn all gray and first? Well, it does, because LLMs learn the first. I think that those are the same intuitions we should apply here. It's just like my view why it learns. I don't know if that's correct.
No, I think it learns patterns. It learns to predict. It learns to predict certain. Yeah. Patterns in the data. I mean, the nice thing about self-supervised pre-training is that you can apply it to anything. You can just feed in. You can even feed in test data. And so, for example, in domain adaptation becomes easier if you don't need labeled examples of your target domain. We could just feed in some traffic from live traffic, and the model learns to represent live traffic, which may have different lighting conditions, which may have mobile phone cameras. Standard problems is you have supervised training data that's maybe from good cameras. Now your end users give you mobile phone cameras that are crappy, that are very different. So you have a domain mismatch problem and domain adaptation problem. Even when you have weak labels, you may not be able to do this with masked autoencoding self-supervised training. You can add your target domain. You can do domain adaptation in this way, which makes the model way more robust and more useful.
Like,
I don't really know. Oh, it becomes so it depending it's a sequence of vectors. I mean, it's a layer. If you look at the MVIT model, for example, it's an encoder that's pyramidal, and then you have a decoder that reconstructs the input, and in the middle you have a sequence of vectors. So it's a 2D representation, but it could also be 3D depending on how you cast it. But it's probably even harder to look at it than then you can look at CNN filters to see what it learns. I don't think we've ever looked at it, or anybody really has. All right. So at this point, masked autoencoders, there's a paper called Masked Autoencoders of Spatio-Temporal Learners. It's sort of a very simple model that can be applied to images, audio, videos, and of course text, that gets very strong results in general on many tasks, but not always the very strongest tasks. So if you have good weak labels, you can beat, and if you have large pre-training data, you can beat masked autoencoding pre-training. But one thing that's very and depending on how you structure it, if you do random masking, you have BERT, and if you do sequence masking, predicting the next token, you have a GPT style model. But one thing that's very interesting for computer vision specifically, and also for video modeling, is because you have such a high masking ratio, you're masking out 90% of your inputs. And yes, in an ideal world, you can you're not masking out everything, but you're rotating some patches. But if you're already masking out 90%, you just really want to forget about the 90% and really only load 10% of your data, or maybe 5% of your data if you have a 95% masking ratio. And in practice, these models are very attractive because you are really only you're loading a video, but you immediately discard 95% of it, and then you reconstruct the original video from a very small part of your input. And so both during encoder training and at inference, you're really only looking at a very small part of the data, so the model becomes much, much smaller. And so these models learn very, very strong self-supervised video representations, but at the same time, they can be much, much smaller when you actually discard 95% of the input. So typical training curves of such masked autoencoder models. Here we're looking at video action recognition. We have the accuracy over time. The blue curve is training a masked auto, training a transformer model for action recognition from scratch. And it goes for 400 epochs. It trains well. It goes. It reaches what is it, 73%. But if you do masked autoencoder pre-training and then do fine-tuning only for 100 epochs, you're reaching much higher performance much more quickly. And of course, you can use bigger models because you have a larger pre-training data set, and you have because you can leave out sort of discard 90% of your resolution or 95% of your resolution during training, you can easily train bigger models. I have some ablations of this masked autoencoder models for videos where we can see for this particular configuration, random sampling works best. If we do space-only sampling, which is sort of the tubes, it works a little bit, looks almost as well. If we do time-only sampling, it drops into this block. Sampling works a bit better. But again, other people find different results here. Then we can try different reconstruction targets, and the simple trying to predict the input pixels with normalization works best, but we can also try to predict various vision features or variational autoencoder tokens. These work almost as well. Different data augmentation. works well. Different strategies work well, but simply random cropping here works best. So complicated augmentation strategies aren't strictly necessary in this particular experiment. And then, yeah, various ablations on decoder width, decoder depth, or how we do repeat sampling of the same sampling to reduce data loading overhead. So I think the message that I'm trying to give here is that different masked autoencoders are a robust way of learning video representations. An interesting thing or variant of this is also mask feed, where we're actually not trying to predict the original input, but we're trying to predict traditional computer vision video features. So we can, instead of reconstructing the image, we can predict visual features such as the optical flow or other gradient derived features from the video signal, which can then give us a little boost because the model learns to reconstruct not just static image, but it has more temporal context. But sort of then we're again specializing our model towards video action recognition in this task. Yeah, I am. That's where I was planning on doing a break. So if we have, yeah, any questions? Yeah, so for computer vision, specifically video, video representation learning, data loading is a huge problem. So we need to take a video, we need to decode it, we need to blow it up into a big an image, and then we throw away 90% of the data. So can we be clever with the way we sample the videos and only load a few videos and then sample differently from the same video and reuse the same data multiple times? And so this is what this means. We can load one video and then sample 10% here and then sample a different 10% here and sample another 10% here. Then I only have to load the same video once, but I can pretend that it's 3 different videos during training, and that allows you to train faster. That's what this sampling means. No, but I'm doing self-supervised, so I don't have any training labels at this stage. The concern is that I only have one video, but I'm learning. I'm using it 3 times, so maybe I'm dropping. Say again? Exactly. I mean, you may not learn as much by looking at the same video 3 times than looking at 3 different videos. But it shows that that's true to some extent, but it speeds up training significantly.
Is it only applied to images or like for video? It can be applied to object flow as well.
Right, it can be applied to object flow. I mean, there's various. They tried out optical flow, various other video features, and you get a small but consistent boost from that specifically for video. Yeah. All right, what time do we want to reconvene? All right. All right. Thanks everyone for coming back. So we've spoken about basic tasks in computer vision, architectures, and representation learning, self-supervised learning. Now, I want to continue to talk about image text learning or vision and language, which sort of was a big topic in computer vision over the last few years. Talk about foundation models and talk about fairness in the second part. So let's jump right in on image text learning. Now, one thing that people realized, maybe even back in 2018, is that computer vision and language can help each other. It's not surprising, but with the large amounts of data that's available, this becomes a really interesting way of improving the training of computer vision models as well. So Dhruv Mahajan and colleagues at Meta in 2018, they sort of took a large data set of images with tags that were available for images. So essentially just hashtags, just words that people had assigned to them, and said, well, can we improve performance on ImageNet classification? ImageNet, of course, is a task where you get an image and you have a label that's sort of an object that's somewhere visible in the image. And they said, well, we don't have a lot of these labels. We don't have a lot of strong labels. I think there's about 2 million strong labels, but we have about 1 billion Instagram images with hashtags. And even if we restrict ourselves to the most frequent hashtags, 1,500 types of hashtags, can we pre-train a model on Instagram and then use it or fine-tune it on ImageNet? And they found, yes, they can do that. Particularly, of course, you can train a much bigger model when you have 1 billion images for training. And then when you fine-tune it, you get much better performance with this pre-trained model over a model that's not pre-trained on 1 billion images. So clearly there is something there. And if you go from hashtags to words and captions, maybe we can learn even more, and we can learn, well, more powerful representations, more fine-grained representations that allow us to do even better image understanding and general computer vision tasks. Now, this is what OpenAI did in 2021 when they published CLIP, contrastive language image pre-training. And this is really, I mean, this work has been very influential in that it showed how image and language can help each other, even in core computer vision tasks. What they did is they crawled a corpus of 400 million web images with captions. So they didn't have hashtags, but they had captions, which can be phrases, which can be sentences, but you really don't really know what's in there. They trained a relatively straightforward model. When they say we're doing contrastive pre-training, well, you have a number of images, you have a number of corresponding captions. You feed them through a text encoder and an image encoder, and the text encoder is a transformer. The image encoder, they tried CNNs and vision transformers, and then you just define a loss function in a batch over this matrix where you're saying, well, the matching captions should have high similarity, and the mismatched ones should have low similarity, so you want to force them apart. This is standard, essentially a two-tower model, which you're also using for recommendations. And yeah, you can do a lot of interesting things with these representations that these encoders then learn, that we'll talk about in a minute. Important thing here is the data quality is really an important part of this approach because the model itself is relatively straightforward. Also, an interesting observation is that the similarity, the CLIP score, correlates to some extent with human estimates of how well an image is aligned with the caption, but there is also extra work happening to measure and improve this alignment between image and text even more. So yeah, I think the way to use this very frequently is to train the visual semantic embedding, as it's often called, using contrastive pre-training, and then create data sets with a classifier from label text, and then you can even use it for zero-shot pre-training. So you can create sentences that say a photo of an object. You can create the corresponding text embeddings, and then all you have to do is take an image, pass it through the image encoder, and find the closest embedding, and you have captioned this image, and you sort of have identified that this image contains a dog. And at the time, this model was the best performing model on ImageNet, I think, and it had performed really, really well on other tasks as well. But the exciting thing really is that you can use it for zero-shot prediction. So you don't need to train a model specifically to predict the dog. It's good enough if you don't need to train a computer vision model to predict and to learn what a dog looks like. All you have to do is create the text encoder, pass the name of your class through the text encoder, create an embedding for what a photo of a dog should look like, and then you can classify dog images. So even if you have rare classes, this model is able to predict it, and even without any image training samples, which is a really new and powerful property at the time. Maybe we want to save a little bit on time. An interesting observation during training is that when they initially trained this model, they didn't expect this zero-shot capability, but turned out that it's really powerful for that. The web image corpus that they were using is much bigger than any other data sets that were out there, except maybe the Google 300 JFT 300M image corpus sets and work by Facebook on Instagram image tags, where the biggest version has about 3.5 billion images. But this doesn't, the text that OpenAI used to train CLIP has significantly better quality captions than the hashtags. So the representations that you can learn from this web image text is stronger than the representation that you learn from hashtags alone, even on a bigger corpus. Text encoder in the standard model is 63 million parameters, but text encoder performance seems to matter less than the image encoder for image tasks. And yeah, they tried ResNet as well as vision transformer models, and the vision transformer works best. One other interesting observation also is that prompt engineering and ensembling improve zero-shot performance. So depending on how you frame your embedding, a photo of a dog or an image of a dog, the quality of the embedding and correspondingly the quality of the classification matters. So in 2021, when the paper came out, I think nobody realized how important prompt engineering would be just a few years later. But looking at this paper again, this was a very prophetic comment in the CLIP paper in 2021. The CLIP model at the time of publication, when the really strong thing here is that the model outperforms on most zero-shot conditions, on most zero-shot tasks. The model outperforms strong baselines, even ImageNet beats it plus 1.9%. One interesting observation, maybe we were just discussing musical notes. The tasks on which the CLIP model does not beat the state-of-the-art is MNIST, which is a small data set, but a highly specific domain. I'm not familiar with many of these data sets, to be honest, but I imagine if you Eurosat its satellite images, maybe FGVC aircraft, maybe some very specialized aircraft database. So presumably, because CLIP was not trained on a lot of aircraft data or satellite imagery, it doesn't outperform state-of-the-art methods on these data sets. But probably if you do fine-tune it or if you build dedicated models that use CLIP on those data sets, you will be able to improve performance. But yeah, on a large number of data sets, this model outperforms strong baselines even without even in zero-shot settings. In few-shot, if you add a small linear probing head on top of the pre-trained model, you can see that the performance quickly goes up again. So zero-shot CLIP has a certain performance, and linear probing, when you give it a couple of training examples on the target domain and add a linear and add a classifier, performance goes up. Unsurprisingly, depending on the backbone, you get different performance, different improvements. Representation. So this then sort of gets to the question of what type of representation does the model learn, and how does this quality relate to the how does this relate to the effort that you need during inference? And you can see that there's lots of different trade-offs between WIT models, ResNet models, other backbones, but a CLIP with VIT comes out very on top, very strong with the highest average accuracy at the most reasonable compute cost at inference. This is being at inference time only looking at the visual model, and so transformers in this case now also beat convolutional neural networks. That's what ResNet is in terms of compute efficiency. Yeah, we've seen that. And yeah, here's a few examples of the classification accuracy that different data sets give you, or the So the biggest takeaway here really is what made this model work. Transformers were important because they run very fast on GPUs. Big batches were necessary to present a lot of negative samples in a mini batch so that you can run the contrastive loss efficiently and have big enough batch sizes, and overall data set size and curation. So a big problem with CLIP was that training data set was not released, so people could use the model, they could fine-tune it, but you couldn't just go in and train your own CLIP model because very few teams had the compute to do it, and you wouldn't have the data to do it. So Facebook published, or Meta reverse engineered the CLIP data curation pipeline recently, and they were able to sort of demonstrate what pipelines, what filters OpenAI had used to collect the CLIP training data and to train the CLIP model. So you are, at this point, you are now able to, I think this data and these filters have been released by now, so you would be able to reproduce a CLIP model, including data curation, and sort of train your new CLIP model on your own domain if you wanted to, or if you needed to do that. So at a core, image and text can help each other a lot. It helps improve the performance in absolute terms and also specifically for zero-shot scenarios. And this directly leads to the development of foundation models because of the requirements in compute and data.
To understand it, hopefully it's well understood by me. Behind the text encoder in CLIP, there's, I think, GPT-2 model, right?
I think I don't know. I think
the reference is paper, and the paper is GPT-2. That's how I remember it.
But I mean, would they use a unidirectional text encoder? Generally, their representation isn't as good as if you have bidirectional intention.
Yeah. Well, I'm not sure. But my question would be like, how this is transferable to other language models? Because CLIP seems to do pretty well, regardless of what encoder we use. Do you think this is something that is inherently in the task that all the text encoder learn very similar, let's say, up to a linear transformation representation? Or otherwise, would you use just the CLIP as it is, or would you rather fine-tune it when using with newer text models, such as Llama 3 or something like that?
I mean, I think you don't need I don't think you need a really strong text encoder here, but yeah, depending on how much data you have and how fine-grained your representations you want them to be, you would need a different scale text encoder. I think the power here is that you can train even a relatively simple text encoder can extract enough information from the typical caption that you get here to provide really strong supervision to the visual model. So if you had, for example, entire paragraphs that describe an image, then you would need a stronger text encoder.
But anyhow, if you wanted to use it as a downstream task, let's say, so would you begin with the architecture of the original text encoder, or you would just say, oh no, let's just train from scratch and use a bigger text encoder? Am I expressing myself clearly or?
So you're saying would you just train it end to end and make it small, or?
No, because for me the text encoder in Clip is rather small and it
Right.
describes small text. And now I would have a text like a paragraph captioning of videos, let's say, or something like that. So I was thinking whether I should like train from scratch a new bigger version of the text encoder, or whether I should just fine tune, let's say, the original one. I don't know whether this is tackled in literature.
Well, you would fine tune. I don't know if you would fine tune the original one, but you would start from a bigger pre-trained text encoder and fine tune or use that for clip training.
Just plug and play, switch it and go.
I imagine, yeah.
Okay.
Any other questions? Yep.
Product and this after the picture extraction, the tag and the image are actually the same like space.
Right. I mean, that's what you do here. You assume that the text in the image should be in the same space. The dot product should be 1 if they're the same, should be 0 if they're not. And that's why large batch sizes are important, that you have sufficient negative examples in a batch to evaluate it efficiently. But of course, you could have false positives. You could have things that are almost the same. But figuring this out getting this right was a big part of the success of the clip training.
I felt the question a little bit different. They are actually using this linear projection after the feature extraction. So we are still like aligning the multimodal space to be the same. And there's a different linear layer for text and different for the image.
So basically, they first do a feature extraction, and then they try to project two different presentations onto the same.
Yeah, so that they align in the multimodal domain. This is true, right? Like, yeah. There are two linear layers.
With the slides where you compared the benchmark, so what was the measure?
Which benchmark? This one or for clip?
And this after this.
This one?
The measure of the set.
Oh, whatever it is. So I mean, they're the relative delta score. So they're saying on ImageNet, we're beating the benchmark by 1.9% relative on mean average. What's it on ImageNet mean average precision?
Classification.
And this is classification, but on other tasks it may also be classification, but it may not be mean average precision. It may be accuracy or whatever it is. Yeah. But the point is that for the majority of these tasks, they're beating those models, relatively speaking, to the baseline or to the state of the art. I mean, now we're using these glue benchmarks where we're also taking a battery of tests, and whatever the individual metric on each task is, as long as we know that 100% is perfect and 0% is bad, or we can easily map it to this, then we just average it and claim that we improved by moving each of those or moving many of those metrics. All right. So yeah, in this sense, CLIP really is the first, what we today call a foundation model, which is really a pre-trained model that you can just use, and you no longer need to do the expensive training step, but you can either directly run it on your target domain and data, which would then be zero-shot tasks, or you can easily fine-tune it on target domains and data, which is then few-shot or fine-tuning scenarios. So this idea of foundation models, and of course it's being pushed heavily by industry players, is to say, well, you have raw data and it doesn't really matter what it is, text, images, speech. You do some training, this results in a foundation model, and then you can do adaptation to many different downstream tasks. And of course, the secret is in training a unbiased representation that can then adapt well to different downstream tasks. So if you did weakly labeled hashtag-based pre-training for images, you could imagine that this pre-training translates well to to image classification downstream tasks, but it may not transition well to captioning downstream tasks or object classification, object segmentation downstream tasks. So this, of course, makes pre-training these representations very expensive, but potentially very useful, but probably out of the reach of universities, and even within companies, there's now only very few teams that have huge compute resources to work to pre-train foundation models. I think Marek is also going to talk about foundation models a little bit more tomorrow.
Thank you. I already have 50 slides, so.
Okay. Similarly to the computer vision talks, I mean, this is a crazy field right now. I'm listing here a few links to foundation models that I found interesting and relevant. We're going to share the slides, so you'll get them later today. You don't have to write this down. But I think before you start using a foundation model, you shouldn't just blindly sort of try anything because somebody tells you this is the latest and greatest. This is what you have to use. You need to understand, I think, a few things. One is the trade-offs between size of the model, speed of the evaluation, the license, how are you allowed to use it? And there's a lot often about open sourcing foundation models, but really open source for a foundation model doesn't really say anything. You need to be careful or understand at least what the license of the data is, what the license of the code is, what the license of the weights are. And for example, within Meta these days, we need to be careful if it contains data from the European Union. We need to be careful if the computer vision model contains data from Texas or from Illinois, because there are certain laws around this. So those are pitfalls maybe that you wanna look at. It's important to understand what was the model trained on, what is the model being tested on? Are the training data, is this related to the task that you want to use it for? The testing data and the testing task, is that close to what you want to use it for? And how can you fine-tune or adapt the model? What are potential biases in the model? So those are questions that you should ask yourself before just going somewhere and using Clip or using Llama or using anything else just because it's the most recent and the biggest foundation model that you can use. Now, what are typical tasks for computer vision foundation models? Well, the simple thing is you can use it to extract embeddings. And so this is like the Clip model. It extracts general representations, which you can use for downstream tasks. You can use those in any way that's useful. Then you can maybe fine-tune the model in various ways, and you can implement your target tasks and by starting from these embeddings. Another way is to do zero-shot classification, where you directly perform the task on the target data, which often scales well to rare classes because the model has been trained on large amounts of data, and you're sort of seeing graceful degradation to rare conditions. And it works even well without further processing of those embeddings. And the last class for foundation models are then maybe promptable large language models, where essentially you no longer extract an embedding or directly apply the model for a certain task, but you ask a question, you ask a prompt to a model, and it gives you an answer. People are sort of starting to create taxonomies here. We're saying we're going from traditional closed set classification to an open world recognition. So you can say traditional ImageNet had 1,000 labels. CLIP now has open vocabulary classification, so you can put in any class label and get an answer. You can go from specialist models where you have dedicated models for action recognition, for object classification, or for segmentation, to generalist models, models that can do many tasks at the same time. And you can go from representation learning, where you get an embedding, to a promptable interface, which is a model that encodes world knowledge through a large language model and can give you not just directly an embedding, but it'll respond to a specific query that you have about the content that you're analyzing. And so people are creating, you can maybe put foundation models in different spaces and say, traditionally we had labels, and this was sort of maybe if we built WIT or DETR or mass-to-former classification. Now instead of having a fixed label set, we have a language interface, and in terms of the granularity of your classification, you can go from something that applies to an image to something that goes to a region, something that goes to an entire pixel. And foundation models push the boundary both on the sort of the type of the semantics of your classification to the granularity of your classification. Microsoft, for example, also put it this way. They created a Florence foundation model, and they're saying that they're going from no semantic classification to detailed captioning of an image, which is sort of a fine-grained semantic task, and they're going from image-level classification to pixel-level segmentation. So they're having the spatial hierarchy, and the current foundation models and future foundation models can cover all of these use cases in a single model. So I have a list here. Don't even try to look at it. If I put it here yesterday, it's outdated today. So I think what we can do in the class later is play with the CLIP model. Typical process in any case with these foundation models is to start with some labeled test data in your target domain, test various pre-trained models, maybe see how you can combine them, see which ones can be tuned, adapted, iterate on that, and just be very careful to see what types of mistakes does your model make, to make sure you're using the your foundation model efficiently and properly. Finally, of course, when you do foundation models for computer vision, the next thing or the next question is, what about multimodality? This GPT-4o, GPT-4 Omni model. It's hard to speculate exactly how it's being built, what it does, but I think it is quite likely that very soon we'll have foundation models that will take anything which is an image, a video, an audio, text, or other data, and output anything in pretty good quality. So what I want to do is describe a few building blocks that for computer vision, but also multimodal, that take steps towards this dialogue, speech dialogue, or multimodal dialogue systems that we're seeing emerging. So one of the any questions so far, or any comments? All right. So one of the first computer vision models maybe was Florence from Microsoft in 2021, where they are also taking text image pairs as training, not unlike CLIP, put a contrastive learning approach between a language encoder and an image encoder, and then put a adaptation models, as they call them, on top of both of these outputs. So they put a classification and a retrieval head. They put an object level representation head, fine-grained adapter head, video representation head, and then trained with these adapters. They trained the models on different tasks, retrieval, classification, and then had a single model that can perform essentially every computer vision task in at or near state-of-the-art quality. And this was sort of the status in 2021, essentially taking a CLIP-like model and just training a large number of adapters on top of it. In 2024, they had expanded this and changed their training approach a little bit, in that they have an image encoder and a text encoder that they're now feeding into a joint transformer encoder, and a joint which then feeds into a transformer decoder that produces all your outputs, in this case as text. So this does not generate images, but it generates text. So you can see this is effectively a multimodal machine translation system, if you will. You give it an image and you give it a text context, and it produces a text output for that. But they're casting all the computer vision tasks as text processing and machine translation tasks to say, what does the image describe? And they're translating it into a description of the image, locate the objects in the image, and they are generating a textual description of the location of the people in the image, and so on. So for a closed set of tasks, this model essentially takes a text encoder and an image encoder that's being mapped into text space, and then we just run a standard translation pipeline, if you will, and this learns a very strong unified representation for any number of for I forgot how many tasks they're doing, but again, they spend a huge amount of effort on curating the data set for this model, and in particular preparing the ground truth in this format. Another very strong multimodal model is the Flamingo model, which was a very strong multimodal foundation model in 2022, where essentially they're also taking images and text as input, and they're taking pre-trained image text encoders that they are combining with essentially cross-attention layers and keeping the pre-trained separate image and text encoders frozen, while they're then training these cross-attention layers from text to predict, not from text, but from scratch, to perform a number of tasks, but specifically image captioning on interleaved visual and text data with very strong results. So a very convenient and powerful technique for building multimodal models is just starting from pre-trained encoders and combining them and only training a relatively small number of combination weights to build a strong multimodal model. Another model that takes a similar approach is Flava, also in 2022, where we are, instead of combining image encoders and text encoders within their encoders, we're combining them with a fusion layer that's later on stacked on top. And we can do image tasks, NLP tasks, and multimodal tasks at the same time, and training the entire model end to end. So the advantage here is that you can keep at runtime, you can keep the image encoders and the text encoders separate, and you can extract the monomodal embeddings from them. So if you need monomodal embeddings in addition to multimodal embeddings, you can get away with running monomodal and multimodal or monomodal feature extraction once and then do a multimodal computation on top of it, rather than having to run monomodal and multimodal computations separately, which sort of doubles your compute. And that's, for example, what Flamingo does, because you have those cross-attention layers, you're fusing monomodal and multimodal early on, and you can't run them independently at inference time. A third interesting approach to multimodal foundation models is COCA, contrastive captions, where in addition to training unimodal models, you are training the model not just with a contrastive loss, but you're also giving it a captioning loss. So you are, in addition to doing something like CLIP, you're also training the joint model to predict the caption. And so you can do visual recognition, classification, cross-modal alignment, or captioning and multimodal understanding in a single model in zero-shot or fine-tuning fashion, which gives a very strong representation of multimodal content. I think these days, however, the most used multimodal architecture and the most used architecture for integrating computer vision models into multimodal models is the Lava architecture visual instruction tuning paper, which really is a very simple way of combining computer vision with large pre-trained language models, where you're saying, well, if we want to implement a model that we can query, we start from a large text language model, Llama, for example, and all we need to do is provide visual information as additional inputs. And so we can take any vision encoder, like a pre-trained clip model or any other image or even video encoder, add a projection layer, and split this into a number of tokens, which we can then feed into a Llama model or any other sequence prediction model to produce a language response starting from an image and the language instruction sequence. So what we, at this point, all we need to do to train is the projection layer that allows us to map the image into the input space of the language model. And we can use fine-tuning or any other training techniques for the language model. And in addition to training this projection layer, and we have a multimodal language model that performs very, very well on a number of tasks. There was a recent paper that takes this a step further, Animal, where the same approach is shown to work not just for image and language, but also for audio, video, and even motion sensors. So if you have like smart glasses, you can take a video, you can take corresponding audio, you can take motion sensor information, and sort of for each of those modalities, train a projection layer, add in instructions and a request, and generate a response, and train this model from pre-trained components, and get very strong performance on essentially any number of tasks that you're trying. So these are very sort of a little bit hacky ways, if you will, to combine multiple modalities together and build foundation models for visual tasks. There are more principled approaches, for example, a chameleon model, which is, again, in this case, it's a decoder-only model. It's trained by separate image and text tokens, but we are feeding, we're taking an image, we're tokenizing it, we're taking corresponding captions, and we're feeding all of those models, all of these data sets into a transformer model, and predicts and train it on generative and reconstruction tasks. So this model can inherently learn image and text representations together. So it's a very elegant model, but in most tasks that we are testing, it does not, at least at present, outperform models that are being trained on separately trained audio, image and text encoders that are then put together and fine-tuned on target tasks. Any questions on foundation models? All right, then let's talk about fairness a little bit. Now, how many of you have background or have thought about fairness in ML and AI? Okay, it's fewer than about convolutional neural networks. So maybe that's a good thing to talk about. So as we are scaling up machine learning, our models become much more powerful, much bigger. It's much harder to understand what data goes in. What are they doing? What are they predicting? And why are they making certain predictions? And then there's a tendency that they are increasingly being used to automate decisions. So, I mean, there's examples of credit scoring, but many other examples where machine learning systems make decisions that affect people directly. So even when we're not only thinking about the training and testing mismatch, we need to make sure that our models make outputs that we understand and that we think are within certain parameters of what we train them for. And so what we want to make sure is that that their decisions aren't based on any factors that we don't want to, because machine learning systems at their core are black boxes. We can't really understand why they're making decisions. And so if in the data that we sample from the world, there are biases such, for example, historical bias, representation bias. We're only using today's data rather than data from the last year. Then the data may be biased. Then the machine learning model may have certain biases. It may only work well for frequent classes. It may not work well for rare classes. Then if we are not reviewing our performance and the actions that we're doing, we will have models that don't produce outputs that we accept, that we want to accept. And so we should, at the minimum, understand why models make not just mistakes, but why they make systematic mistakes that put certain groups of people at a disadvantage. So one seminal paper here was Gender Shades, where a team of researchers took commercial gender classification systems and tested it on a number of data sets. And they found that darker skinned females are the most misclassified group with error rates up to 34%, while the maximum error rate for lighter skinned males was 0.8%. And so, of course, the results you get will depend on your test data. Maybe on other test data, you won't find these differences. But now imagine if this output was used in systems that assign credit scores or make other automated decisions. So what you need to do is really make sure that systems are fair and you don't systematically put certain groups of users at a disadvantage over others. And so here, the problem is not that the model wouldn't, say, classify hats better than shirts, but the problem is that the model would classify certain users, treat certain users differently from other users, and users in the sense that anybody whose data is being passed to the system is a user, not if you're actively wanting to use it, but if a company runs a system on your data, then you're a user of the system and you want to make sure that the system is fair. So there is not a single definition of fairness, at least not that I'm aware of, but what I want to, here's I'm giving you a couple of pointers where you can read up on definitions of fairness. To me, all useful definitions share the same fundamental idea that a fair process shall treat all involved parties justly and equally. And so this means that no matter whose data is being passed to a classifier, they're being treated equally. So they're getting the same quality of classification, the same quality of service, the same quality of an outcome. There are a number of approaches that try to quantitatively measure fairness, which is a good approach because then you can at least try to iterate on your models and improve the measure if a new version of the model has better performance than the previous model. And one example of this would be per group classification accuracy, so that if you can show males have an error rate of 5% and females have an error rate of 5%, then that's an example of a fair classifier. While if you have 5% and 10%, that's probably not a fair classifier. Now, how can you solve this? Well, maybe one answer is you can't. It's just in the data. But that's, well, a cheap way out. The perfect solution may not exist. You may not have enough data, budget, and time to make everything equal. But that's not a reason not to try. And so what you need to do if you're running classifiers, and particularly in computer vision, is take a user-centric approach, see whose data will be used in this classifier, less than a technical approach, and say, oh, I want to make sure that dogs and cats or hats and shirts are being classified equally correctly. You want to make sure that the people whose data is being fed into a classifier are being treated equally well. And then you need to measure the performance metrics at a group level, not just overall. And if you find differences, see how you can mitigate and reduce those. I want to point out that there can also be you can also argue that fairness needs to be both present at the group level and at an individual level, and these goals can conflict, but there's frameworks that allow you to work towards a resolution. In the US, there are anti-discrimination guidelines even that you can use to inform your decisions. So when you say which groups are there, is there just men and women? Are there other groups? Well, in the US, there are certain groups against which you legally cannot discriminate, and so that's age, gender, apparent race. So at a minimum, you should test your systems against biases on age, biases against gender, biases against apparent race, and resolve any problems. Once you have identified problems, once you have identified reasons, what I don't want to go through, or I don't have enough time to go through a full list of the things that you can do, but well, you could collect more data. You can correct annotations if they are faulty. You can add annotations, for example, for rare classes or classes that don't perform as well. But you can also pick other algorithms that are less sensitive to biases, and you can retrain your models so that certain rare classes, for example, don't fall off as much as majority classes. So even if some tasks are inherently harder, some decisions are more difficult on the data, the user doesn't know or care about this, so you want to get this right. If now with foundation models and larger models, you cannot even start from the training, and you may not have the resources to train a model, test a model from scratch, then the standardized or a good minimum approach to ensure fairness and to understand what your model is doing is this model card approach that was proposed a couple of years back, where at the minimum you need to document how certain models perform on certain data sets, how the model was tested, and which biases exist in the model. And so you can see that for models that the teams release, they are describing how the model was trained for, what use the model is intended for. Is it, for example, is it intended to be used on images of young people, or is it only intended to be used on images for adults? And then which metrics were used to evaluate it, which data was used, and then it shows some here, for example, the false positive rate for old males, old females, young, old, young, old, young, female. So you can understand what biases and what differences in performance are present in a certain model for certain groups of users. Yep.
Is there an arbiter of this? Like let's say I have this report, but I use the biased data set to evaluate on. So I can seem like I'm pretty non-biased and fair. But so how deep does this go? Is this for now just to like goodwill of the company to show like we are already trying, or is it like somehow legally bound to system or?
Well, I think you are doing your best until somebody sues you. I think that's the yeah. I mean that's the point when you need to document and when you need to demonstrate that you've done the reasonable effort and you've done a whatever is possible according to the state of the art to not discriminate against people.
Okay, and in this case, it's a follow-up question, because what if by accident I am fair? You know, I haven't done anything to try to be fair, but somehow I come up fair. So then it's okay, right? So I do not have to, because I cannot prove that I have done anything to be fair. It just happened. It just happened by accident, let's say, or.
Well, okay, if by accident.
So I can still be like I can get into problems, even though my system can be evaluated as fair. I still can have problems because I haven't done anything.
So yeah, I mean, you couldn't, if let's say you're a small company, if you don't have the documentation, nobody would buy your small company. At least I hope.
Okay.
So because they want the documentation that you're fair, and that you should produce documentation to demonstrate that you've looked at things and that you are sure that reasonably certain that you are fair. If the system works, people may not sue you, which is obviously good, but you don't know.
It starts to be a problem, let's say, at scale. So if I do something, you know, for my friends and then it's a small project, it's okay. But as soon as it grows and starts to become like the Facebook or X,
right, then it becomes enforceable and it becomes a legal risk, because I mean at Meta we are very aware of, or any big company is very aware of these risks, and we are documenting internally. We're measuring what systems do, because I mean, if things happen and somebody can prove that you are discriminating, that becomes a risk for the company, and you want to avoid that. So as a university, that risk is lower, but you should still do the right thing and understand what the problems are, understand what the potential solutions are, and design things the right way.
Defines the risk categories. Like recommendation system is variable risk, but biometric identification is high risk of unequally distributed people, and therefore it should be very low.
okay, so it's similar in US. Let's say you have some guidelines. Here is an act. So I don't know whether it's like whether we are legally bound to it. It's just a recommendation also, or a guideline.
Last year in European Parliament, we have quite challenges.
Okay. And does this discrepancy happen? Like, is it very wide between US and Europe? Because I think Europe is very, very much stricter on these issues. So then, what about companies like Meta? It seems that they are working on it, but will Meta split, let's say, into here's how we do it in US, and here's how we do it in Europe, and maybe in future it will like become so far apart that
yeah, I don't want to. I don't want to speculate, but yes, there are guidelines that European or the EU doesn't want EU data to be used in the US PID data. So there is certain things that we can not do already. And of course, the argument is that this degrades the quality of a Facebook service in the EU, but that's what it is. And you may have to build different systems for different targets, or you may have different documentation requirements for different regions. It's not it slows us down, but I think we need to, in this case, technology is ahead of legislation, and this needs to be understood, and we need to get, as a society, we need to get this right. We need to make sure we don't just do what's technically possible. I mean, we have speed limits for cars for a reason. So we need to do something like that here as well.
Unless you are in Germany.
Yeah, I think that's we don't have it technically, but in practice we have it on 85%, and then there's always the law still says that you have to have an appropriate speed, and sometimes that maybe it's rare that it's 300 kilometers per hour. All right, so I think this concludes my talk. I sped through the foundation models a little bit more than I originally planned, but we are on time. Any questions?
Problem with fairness, like is there any particular modality with kind of fairness issue? Does multi-model tends to exacerbate or alleviate some of the problem?
I don't know. Good question. I think, I mean, I guess it depends. If you have a specific task, a specific system, you could probably trace back the source of error and attribute certain outcomes to different modalities, and then say these outcomes are primarily caused by this modality. Would be an interesting study, but I haven't seen that. No. Anything else?
That would lead to a successful
Well, I mean, we need to have the compute and the data, and I think architecturally, I mean, we know how to pre-train strong text encoders. We know how to pre-train strong vision encoders, and we can bring them together using a variety of approaches: Flamingo, Flava, Lava for generative models. These models give surprisingly strong results, I think. Building models that can ingest any type of modality into one single model, so like the chameleon model, they tend to perform worse than these sort of late fusion models for now. right? So you're taking a strong text encoder, you take a strong video encoder, you put it together using Flamingo architecture, and you have a very strong multimodal foundation model that you can fine-tune on downstream tasks. Or you use the Lava architecture that I think many of the current LLM models, multimodal LLMs, are based on something like that. Certainly the open source ones are based on such an architecture, and it gives us very strong results. Figuring out how to put every modality into the same space and build a trainer foundation model. Probably, maybe OpenAI has already done it. If not, it'll take another year or two. But then I think we will have a pretty strong promptable language model that can provide very detailed descriptions or about images, text, whatever you want. Is this a computationally feasible approach? I don't think so. So I think for many tasks, we will continue to build much smaller models that are designed to solve specific tasks such as segmentation or captioning or I don't know, object detection. But maybe we're gonna train them on using labels that have been generated by very powerful, very strong foundation models that are multimodally trained foundation models. Does that make sense? But I'm speculating here myself.
Budget we need if we want to do our own multimodal LLM. If as a researcher I want to do it, let's say we just like some data like mainstream, what should I aim for as a researcher?
I mean, I've stopped tracking the compute requirements of Llama pre-training or any other pre-training. I mean, they are several thousand GPUs for several months, and once you have such a model, you can scale down. You can train smaller models by distilling them. But you need to have a strong teacher model initially. So I think it's I mean the reason Meta stock price went down 10-15% earlier this year was because we were telling people how much we're going to spend on compute hardware. And the fact that we were actually able to spend this much money on buying new data centers surprised people, and this made profits go down, and it made the stock dip. I mean, it's insane.
First product budget, but what if I want to use this model inside of the devices? What are the correct steps? Is it possible with multimodal LLMs, or do we need to put the model on cloud devices
Well, any answer I give now will be out of date 2 weeks from now. I mean, you would imagine that if you had a mobile device and you want to run an LLM on the mobile device, it's not currently possible unless maybe you have the, what is it, iPhone 16. But even then, it'll be a scaled down version of a bigger model. But I mean, so many people are working on making models smaller, quantization. So many people are, you're discovering tricks on how to distill models from bigger teacher models. The more you unify the architecture, the easier it becomes to design hardware specifically for that architecture and to implement models efficiently and to let the model figure out where it needs to spend the parameters. So, I mean, if you have a separate image and text encoder, you need to design both of those encoders and say, oh, this is how big I make this is how big I make this. And then if you get it wrong, you end up in a suboptimal solution. If you have a unified architecture, you have much more hyperparameters to pick, and the model figures out where it needs to spend parameters. All this is happening, and it's happening very fast. So, of course, presumably, a lot of the compute happens on the cloud now, but so that companies can collect data, can collect and can run bigger models. But as these things scale, nobody wants to build the data centers to run the inference. So if this can be pushed to the device, it will be pushed to the device, and it will. I mean, it's happened with speech recognition. It'll happen with large multimodal foundation models. I have no doubt.